Hi, I am Pablo, and with Theresa, we've been working on the project called Matrix Exponentiation on GPU for the deMon2k code. This is the overview of the presentation, where we will first see the matrix exponentiation and deMon2k. We will see the GNC supercomputer, and finally we will talk about our matrix exponentiation implementations. So first of all, deMon2k is a software package for density functional theory, and our goal in the project is to develop a very efficient implementation of the matrix exponentiation, which is a computation that takes place inside the deMon2k. So inside our node of the GNC supercomputer, we have two Intel Xeon Gold 6248 and four NVIDIA V100. So this is the hardware we've been working with, and this is the hardware we have used in the benchmarks we will see later. So the matrix exponentiation has different ways to compute it, and we have chosen two of those. The first one is the Taylor series. To compute the matrix exponentiation using the Taylor series, we have this expression, which is basically the sum from n equal to 0 to infinity of a to the power of n divided by n factorial. So the Taylor series is computed using matrix multiplication and matrix sum. But since the matrix multiplication is much more heavy than matrix sum, the core of the Taylor series is the matrix multiplication.
The second approach to calculate the matrix exponential is the diagonalization. At first, the matrix A is decomposed to a product of three matrices, Q, D, and Q inverse, where Q contains the eigenvectors v1 to vn of the matrix A, and D contains the corresponding eigenvalues, lambda 1 to lambda n, stored at the diagonal of D. With this decomposition, the calculation of the matrix exponential is very easy. Only the values of the matrix D have to be replaced by the exponential of each eigenvalue. As a first step, we implemented these algorithms on a CPU. We used the BLAS library, the basic linear algebra subroutines, and the LAPACK library, the linear algebra package, from the Intel Math kernel library. Here you can see our benchmarking results. We tested the averaged execution times for different matrix dimensions. The first figure, you can see that the algorithm based on Taylor expansion is slower than the diagonalization on one core. The figure below shows the execution times for the CPU implementation running on 40 cores. One can see that the roles have changed, and the Taylor series expansion performs better than the diagonalization. The next step to improve the performance was moving to the GPU. For these implementations, we used the cuBLAS and the Magma library. cuBLAS is an implementation of the BLAS library for GPUs, and Magma, short for Matrix Algebra on GPU and multi-core architectures, is a dense linear algebra library, especially for GPUs and hybrid architectures. Our benchmarking results on a GPU show that the algorithm using Taylor expansion is very well suited for GPU architectures. This is not surprising, since a large part of the execution time is spent on matrix multiplication, and this operation is very efficient on a GPU. The algorithm using diagonalization performs very well for large matrices. We obtained a remarkable speedup with both versions, compared to the CPU version using 40 cores, as you can see in the second figure.
And finally, for MultiGPU version, we couldn't finish a efficient implementation of the diagonalization, so we just have the Taylor expansion. And as we can see in the results, we have a very efficient implementation, since for the big instances like 20,000 and 10,000, we have perfect speedup, since we have 4 GPUs in GNC and we obtain 4x speedup. Thank you very much for your attention. I hope you enjoyed the presentation, and bye bye.